So let us now create the workflow. Before we create the workflow, we will see where to find the components. So if we navigate to this tab AM, here we will find the subcategory Amphyon. So if the add-in is successfully installed, you will find all the components here. So let us now move to the workflow. So the first step is to import the part on which we want to perform the process simulation. So it has to be a mesh. In this example, we already have the internalized data. That means we have the part already here. So here it's a simple geometry with one of its regions hanging as a cantilever beam. So we will use this simple example to learn how to create the workflow, and later the same workflow can be used for any other geometry. So we also need the support structures to perform the process simulation. So here we have like 3 different kinds of supports. These are volumetric supports, and then we have thin wall supports that look like this, and we have a combination of both the support structures. So here we can select different kinds of supports that we would like to use now. So let's go with the combination of both the support structures now and move to the next step. So here we have the part and the support study now. If we would like to import the part and the supports, we can also do that by using the component import geometry, and here we can select the STL file, the geometry and the supports. So the next step is to create the octree mesh using the Amphyon octree technology in order to perform the simulation. So we can find the component here, Amphyon octree mesh. You can also search for the component here, Amphyon octree mesh, and use like this. So as we see, the inputs are the part and the supports, and then it will create the mesh. So let's hide this imported parts and we will see the mesh like this. So this is the octree mesh. As we can see, there are like a couple of inputs on this component, so let's understand them. The first one is automesh fineness. So this represents how many elements has to be created. The range of this parameter is between 0 and 10. As we move more towards 10, it creates a really fine mesh. So now we can see with the intermediate value how it creates a fine mesh. So now we can see the mesh accurately represents also the thin wall support structures. For the thin wall support structures, we define the wall thickness here. So based on this value, it calculates the mechanical properties. So hence, it's not really required to have a fine mesh and have a separation like this to represent the support structures. If we reduce the value and create a coarse mesh, it looks like the support structures are thickened up, but it will not have any adverse effect on the simulation results. So let's go with the coarse value for now and move on to the next parameters. So we can also define the custom mesh size. Once we turn this option on, we have element width and the layer height that we can define. So based on these two values, it defines the minimum element size that has to be used. And we also have a couple of other parameters here, improving surface approximation. So if this parameter is turned on, it will be used when we create the pre-deformation analysis. That means the pre-deformation part. So by turning this option on, it will increase the number of elements by around 25%. We can also turn this option on, avoiding large elements. So in this case, the ratio of the largest element to the smallest element would be limited. So if we turn this option off, it would only result in 2% less elements. So we can use this option. And here we have to define what type of supports are we using for this analysis now. So here we have volumetric and thin wall supports, but in our case we have both the supports. So as we can see here, 0 represents the volumetric supports and 1 represents the thin wall supports. We can combine both 0 and 1 using this component merge, and we can input this here, and then it identifies that we have both the support structures. So here we can see the output is the mesh, and the layer count. So the number of layers will be filled step by step while performing the simulation. We can see the result once the simulation is completed. So this is about the meshing. In the next session, we will perform the simulation.